Okay, so what we are going to do is just the extension of the Gauss's law that we learned last time, and it's just like a good applications in the sense that it's going to drag everything that we have learned since, I mean, all the concepts about the Gauss's law, the flux calculation, and the potential difference. And eventually, it's going to lead you a new thing, which is, well, a device that we use a lot in a lot of appliances, electronics, and all this stuff around us, which is the capacitor. Right? So that's what we are trying to study today. And I think the goal of today's lecture is just simply allow you to calculate the parameter that identify how I mean we're going to define what is the determining factor of the capacitor, and that parameter is called capacitance. So as the name imply, is the device that is used to store charge. So that's why it's called capacitor. It's like a capacity to store charges. And the capacitance is the indicator saying how big is this capacitor. So the bigger the capacitance mean the bigger that it can store charges inside. That's it. It's a concept is very simple. Okay. But we're going to learn the some sort of like an internal working like a constructions of the capacitor a little bit. And then we are going to do the Gauss's law, and that's it. We're done. All right. And the good thing about this one is I am going to tell you exactly one question in the exam. So that's sort of like an incentive of looking at study this lecture over here. Okay. All right. So the concepts of capacitor is very easy. If you look at this one, you can see that there's one side of the device is positive Q, the other side of the device is negative Q. So this is sort of like suggesting that initially is going to be like a neutral. Okay, so it's just like think of something neutral, and then eventually, if you can move charge from one piece to the other, so it means you can deposit positive Q on the left side of the device, then you're gonna leave the other side negative with the same amount. It just transfer the charge from one to the other. So you have like an unequal distribution of charge. So one is positive, one is negative, and it's automatic. Once you do that, you generate potential difference across automatically because of course you know that the positive charge has a high potential side and the negatively charged area will have a negative potential side. So you're going to generate potential difference anyway. And just a quick note, if you have V and delta V, they are the same thing. Okay, I think maybe people just feel lazy, don't want to keep drawing the delta sign all the time. So they just drop the delta and say the V is a potential difference. All right. They are the same thing. All right. So what we have over here is this. This is the like a main diagram showcase the internal construction of a capacitor. But in reality, of course, it's going to look like this. All right. And we're going to sort of like look at the internal portion of this one, like how does it look or what kind of device or material that you need to build something like this. Okay, it's I mean it's very common looking in the circuits and everything around you. It has this kind of stuff on it, and now we know it's capacitor. Okay, so by having this charge and the potential across, so that's what you have. Now to define the ability to store charge is very simple now because this is what you want. You want the Q to be big. And of course, you want to be big given that the V is as small as possible because smaller the delta V, the easier for you to move around things, right? That will make a lot of sense. So that's why we can simply define the capacitance, which is the ability to store charge, by taking the ratio between the Q and the V. That's it. So that's how easy it is. All right. Or you can rewrite this in terms of like the charge is just the capacitance multiplied by the potential difference across. Done.
Okay.
All right. That's how easy it is, guys. So well, there's only you and me at this point. But anyway, but that's what it is. So this is the definition of the capacitance. And look at the units a little bit on passing. The unit of the charge is coulomb. The unit of the potential difference is volt. So it's the coulomb per volt. That is the capacitance unit. We have a special name for it we call farad, all right, in order to microfarad. Okay, already. So with that in mind, now let's take a look at the simplest type of the capacitor. So what can we build that thing? So the easiest way is probably this. You need a material that can move charge around easily, and so mostly are metal, conductor, whatever, that can allow charge to move. And second thing is you want two sides, because eventually you're going to put one positive into one side of this, the other side is going to turn negative. So you just have two pieces of this. So the easiest construction that you can get is parallel plates capacitor. It's flat sheets of metal, think of it that way, put them side by side. That's it. Once you apply the potential difference, then you can move the charge around. So you start from the neutral plates, and once you apply potential difference, there will be rearrangement of the charge. So one will turn positive, the other one will turn negative. And then you disconnect that potential difference, you have a charge stored in your device. That's it. All right. But anyway, you probably say, well, John, well, if flat piece of thing might not be easily being used, so you probably can do a sphere if you like. So as long as you have two pieces, it works. You have an inner spherical ball. It's supposed to be like, it could be a shell, right? It could be a thin shell or it could be a solid ball. But anyway, you introduce one surface and the other one parallel to it, but it's parallel in a three-dimensional case. So think of it like you have a concentric sphere that can be built as a capacitor as well. Another geometry that might be possible is, all right, you can do like a coaxial cylinder. So you have like two pieces and then you wrap around an axis. So you have like a central axis over here. And then, yeah, that's fine. So this is it. So these are the three main geometry of the capacitor that we're going to study. Okay. And starting from the top one, which is the easiest one, then we are going to calculate what is the capacitance on these three. Okay. And you will see how easy it is to do. And not only that, we're going to use Gauss's law to do that as well. All right. So we break this thing down into three steps for you. And once we're done with this, that's all I need from you today. So that's not a lot. I decided already that I hope while having the lecture during the holiday or in I don't know, you are supposed to be like I don't know, resting day, and that's, I'm not supposed to push too much here. So there are three steps process. Okay. First, you want to figure out the electric field between. All right. Because now you will see that one place is positive, the other place is negative. So you pretty much guarantee that there will be some electric field in between, because electric field points from high to low or point from positively charged particle to negatively charged particle. So that means first steps, you will figure out the electric field in between. Now, once you know the value of the electric field, go back in the previous lectures, we already learned. Once you know the field, you know how to calculate the potential from the field using the definition of the potential difference. So you do the integral of the E along the some displacement along some path. And that will allow you to determine the potential between the upper plate and the lower plate, or the upper surface or the outer surface and the inner surface, to get to the potential difference. See, that's the main thing that we want. We want the potential difference. Once you get the potential difference, if you know the amount of charge and you know the V over here, V and delta V are the same thing, you just take the ratio. So the step number 3 is going to be the easiest because you don't need to do anything anymore. You take the potential difference that you got from the second step, you get the Q that you probably learned on the way to get to that, take the ratio, that is it. That is the capacitance of that capacitor. Sounds cool? All right, so that's the thing that we're going to learn to do today. If you learn how to do this, bam, that's it. All right, and at the end of the lecture, I will leave one as a question in the final exam. Okay, let's take a look. The difficulty is going to be the first one. The reason is because during the Gauss's law study, we only took the example of the spherical shape system. So you only created the Gaussian surface to be in the form of a sphere all the time. But now the shape of the parallel plate is not a spherical shape anymore. It's a plate. So now that suggests us that the shape of the Gaussian surface is supposed to be other than sphere, right? Because I mean, a sheet or like a flat piece of metal or flat piece of charge distribution on a plate shouldn't distribute it in a spherical manner whatsoever. So we're supposed to pick something else. All right. So that is something that we need to apply Gauss's law on an isolated conducting plate. Let's try that one first. Okay. This is going to be the hardest portion of today's lecture. But once you get this one, everything else is just simple. I hope. All right. So we should. All right. Let's take a look at that. Now, I mean, once again, to learn this one, I think the easiest way is to do together this thing from scratch. Okay. Because if you just read through this slide, then you probably don't get a feel for what is going on here. So I'm going to once again add a page and see how things go. So the easiest way for you to do is just look at this sideways, I think. So let's see how it goes here. So if I have a flat piece of metal, so I mean, oh, we can draw some thickness on it, of course. All right, that's fine. Okay. And then let's say that I have a positive charge distributed across this one uniformly. So this is a side view, right? We look edge on. We look from the side. Okay. So if you look in the three-dimensional, of course, it's going to look like a plate like this. Let me draw it. There you go. All right. So that's a positive Q all around. There you go. Very nice. And now, because it's a two-dimensional piece of conducting material, usually we love to define the density, right? We saw the lambda before is a charge per length. We saw the rho before last time is a charge per volume. Now we're going to do the charge per area. So let's name this sigma. It's a charge per area. So it's good. Every time that we have density, it's very easy and very convenient to convert to amounts of charge. So that's good. So let's work on this problem based on the known value of the charge per area. Now, by symmetry, right? Remember we did the Gauss's law. Everything that we use, we're gonna always use the symmetry argument all the time.
Okay.
So what we want to argue now is what kind of electric field supposed to come out from a plate like this. Back in the day of the spherical symmetry, you said electric field is supposed to point out in the radial direction in all 720 degree or whatever around it everywhere. So it's a radial directions for the electric field uniformly distribute across the space. But now we have a plate. It's a two-dimensional plate. What do you think electric field is supposed to come out of this? So imagine this. For simplicity, we will assume that the plate is big, because if it's not big, you kind of know that, Ajahn, if it's not big, the electric field towards the end of this will just, diverge out and will go crazy toward the edge of this plate. Electric field at the edge is going to go crazy. But if you have a straight plate that you can ignore the boundary of this one, then I think things will be smoother, I hope. All right. So the way that I can show you, I think instead of, explain this and that and on and on. So once again, I want to show you by taking you to the simulation. All right. So if you want to go along with me, then I will place a link over here. All right. It's the same place that we did before. So I'm going to take you to the same simulation. So where is that simulation? It's gone already, so that it's fine. So let me point that out to that simulation one more time. Here you go. This one here. Bam. Alrighty. So what you have over here is now the simulation that we learned before. Let's try that. Okay. So what you have over here is now I'm going to arrange the charge, okay, into something that, okay, let me, oh, that's fine. Okay. So what we have here is, can I do full screen? There you go. All right. So what we have over here is, now I'm going to arrange the charge. Start looking at this. If I have only single charge, it's right there. That's fine. Now I move next one to it, next one to it. And you look at the progression of the electric field around, and you start to see the pattern that come out of it. See, of course, I mean, if you really do the detailed calculation, it's going to be like summation of all the electric field vector around, right? But this is what it start to build when you have tons of I mean, it's not electron, sorry, tons of charged particle lying around here. You know, let's try to be straight here. All right. Using my finger is going to be a little bit big here. All right, there you go. You seeing something here now? I hope. More. Yeah, here we go. There you go. Okay. All right, you can do it yourself. I think if it's gonna take, I don't know, it's gonna look better. All right, here we go. See? So when you keep doing this, and the more that you put in, I mean, you want to put them in like a very uniform way as well, because you don't want to have them non-uniformly distributed. But you start to get the feeling of what's happening here is the electric field line toward the center of this charge plate. It's like a piece of charge. It's like two-dimensional sheet. Think of it like a sheet of charge, but this is like a side view of this. Electric field supposed to come out straight, perpendicular to the sheet itself or the plate itself. Can you see this? And you can see that toward the top part of this and the bottom part is curved out a little bit, of course, because that's the boundary of the plate. But toward the center, it's pretty straight out. Very nice. Okay, so that's the logic over here that, okay, as long as you don't worry too much about the boundary or the rims of the sheet, and you look into the middle portion of this plate, electric field supposed to come out in the perpendicular fashion to the plates. And by symmetry, that makes perfect sense because you get cancellation from the top part and the bottom parts of the sheet. So the vertical components of electric field supposed to cancel each other out as long as you assume that the sheet is very big. So the only non-canceling part is the one that is pointing outward. So that's why you will have a leftover pointing away from these sheets. Is that cool? All right. So by looking at the simulation, I think that's a lot easier for you to do this. So that's why what I can now say is the electric field that coming out from this, as long as you ignore the electric field due to the rims, it's going to come out perpendicular, 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 perpendicular on both sides, of course. And come out like this, come out like this, come out like this. Very cool. Neat. All right. And if you want to draw it in the 3D, it's going to look pretty much the same. It's going to look like that. Okay. That's nice. There you go. All right. Very cool. And now, next question. So we already concluded that the electric field direction is supposed to be just straight, horizontally in this particular drawing over here. Next question is, what shape of the Gaussian surface should we use? Right? Remember, we want to pick the surface that allow us to calculate flux on it to be like a very simple way, sort of a simple calculation. We don't want to integrate this. We don't want to integrate that here and there. So what should be the shape for us to be able to calculate? Can I move this? Here, there you go. No, I only want to move the upper portion there. Here we go. One more time. So what should be the shape of the Gaussian sphere that we should build based on the known direction of the electric field? I mean, the electric field left and right supposed to be the same, guys. All right, this it's supposed to be the same, right? By symmetry. Okay, sorry, I didn't check the size. I mean, actually, it's not stop here. It's just going all the way. It's going all the way. Going all the way. Here you go. All right, better. So by symmetry again, well, Ajahn, if you really want to build a surface that make things easy. So, well, I know that now electric field is pointing horizontally. So first, I think I'm going to build something perpendicular to it. So the surface will look something like this. Here, if I have a surface that is perpendicular to the E, the calculation is going to be simple because E piercing through the area in the perpendicular fashion, the flux is just a product between them. Bam, that's perfect, right? But then we want a closed surface. The surface needs to be closed. So we need to build something that is closed. So let's build a box around. So the reason that I built a box around because I know that there will be no flux through the top, the bottom, the front, and the back side of this box. There's no penetration. So see, this is the clever way of picking the surface that allow the next step calculation to be super, super easy. So the only surface that concerns me in the next step is going to be just only the surface that is on the right side of this one. Isn't that cool? All right.
Okay.
And now, but Ajahn, wait. You have the back side of this one as well. Well, okay. All right. If I want to have that, then I can extend this box toward the back side of this and wrap it. And now I have a closed surface. It's a closed box. And don't forget that the electric field also point backward as well. There's a back side of this whole thing. The whole business over here is happening on the back side as well. No change. So when you look on the side, the box that I'm building is going to look like this. Here we go. There you go. That is my Gaussian surface. Cool. Alrighty. So let's do that. So what we want to do next is just what John, go for it. We just want to calculate flux on this box right here. And what we said is, okay, you have the top, the front, right? Keep going. The bottom, the back. These are all zero. Okay, the top is here, nothing. Okay, the front is here, nothing, no penetration. The bottom, no. The back, no. So the only two that left for you to calculate is the flux on the left and the flux on the right. So the left, let me highlight in blue here. There you go. And the right is in blue here. There you go. See? So those are the only two surfaces that's going to get non-zero flux. Nice. Okay. Maybe I'm just drawing too big. Oh, is that right? Okay, that's not too bad. It's not in scale somehow. It's like the back side is larger than the front. Okay, I'll try to draw it in scale a little bit here. Okay, here we go. All right, so that's what we want. The flux on the left, that's what surface we want. And the flux on the right, that is another surface that we want to calculate the flux. Okay, and these are all gone. Nothing, 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 nothing. Okay, so let me highlight here on the left, on the edge on view as well. So these are the two that we want. Flux on the left and flux on the right. There you go. Very good. So far, so good.
Okay.
So I hope this will give you another kind of geometry in contrast to the one that we did with the sphere. That sphere, we always build a sphere, right? With the spherical symmetry, we build a sphere wrapping around the charge. Now we have a plate. So we do a box. And we hope to calculate the flux through the surface that is perpendicular to the field that coming out of the plate or a sheet over here. All right, so how much is the flux on the left, guys? It was just okay, Ajahn, that's easy because this is just a flat surface over here. So a vector is going to point perpendicular to it and in the outward direction. And on the right side, the area vector is going to point to the right, perpendicular to it. So it's kind of cool. All right, so I can overlay this on top just to make it clear here. That's the A vector. Let me put like a big one here to showcase that. Here we go. There we go. That's big. All right, so that's it. So that's my A vector on the right and A vector on the left. But Ajahn, electric field vector also point out over here, and out over there. So that means electric field vectors already point in parallel direction to the A vector. Whoa, isn't that cool? So that means if you look on the right side of this one, E, it looks really dirty now, but E and A are already pointing in the same direction. And if you look on the left side, E and A is also pointing in the same direction, pointing outward. So that's good. That's what you have over here is, okay, on the left, it's going to be E times A, left side, cosine 0. Flux on the right is E times A on the right, cosine 0. They're both 0 degree because they are parallel to each other. Okay. And now, because you didn't say what is the area of this one, let's call this area A, and they both must be the same A. So let's call it E on, I'm sorry, A on the left magnitude and A on the right magnitude to be same value, is the same surface size. So it says A. So it's going to be twice E A. And that's it, guys. You are done. That is the flux from a two-dimensional sheet of charge. And one thing that you can notice right away, Ajan, if you really want to figure out some sort of like, you know, the electric field, you just use the Gauss's law, right? Here's the key. Remember, we equate this to the charge enclosed divided by epsilon naught, right? Okay. You already done with the flux calculation is 2EA. Gauss's law said is going to be equal to the charge inside this Gaussian surface divided by epsilon naught. Here comes the question. How much charge is inside this box? Well, John is here. That's it. Let me put like a blackened area over here just to emphasize. You see? Beyond this box, you don't care. Here, that's the blackened portion. That right there. You only care about the charge that is inside this box. Everywhere else beyond this, even though it's still on the sheet, I don't care. I only care what's inside, only the one that included inside the Gaussian surface. So, because we already knew the rho, the charge per area, and the area over here is still A anyway. So the blackened area, the shadow is still A. So let me put A over there. See? So that blackened area is still A. So what is the charge there? It's going to be sigma A here. Does that make sense? Yeah, sigma is a charge per area. You multiply by the area, you get the charge back. And the good thing about this one is it's an A cancel. So this is the reason why you don't care about the A. You can pick any shape of this box. You can be a rectangular shape over here, or you can put like a circular shape if you like. You can build a circular shape if you want. As long as your cross-sectional area is A, they're going to cancel out. I don't care. So that's it. You're only left with just the sigma on the right-hand side. And that's it. From here, you can conclude you left E on the left and you bring 2 to the right, sigma over to epsilon naught. And that's it, guys. You have already completed how to calculate the electric field at the point away from a two-dimensional sheet of charge.
Okay.
So cool. And of course, some of you might just want to, why don't we use Coulomb's law? We don't want to do that, because if you want to do Coulomb's law, you have to do, dq, and then kq over r square, and then you do kq over r square, you do kq over r square, kq over r square, and don't forget you have to sum all those vectors together. It's gonna be like a crazy two-dimensional integral, along with the vector in mind. And I mean, it can be done actually. And actually in the textbook, they did that too. But of course, by going through the Gauss's law is much easier. And the electric field is just simply sigma over 2 epsilon naught. The final result is super clean. Okay? And one observation that you can notice from here is, this is very cool. It has no distance dependence at all. Does that make sense? There's no r, there's no distance from the plate. So from the result, you can say no matter where you are, you don't have to worry about the distance from the plate. You can standing here, you can stay a little bit away, you can go out here, because we have the pre-assumption that we assume that the plate is big, the sheet is huge. So you can stay close, you can stay away from it, you can move back a little bit. Doesn't matter. The electric field is pretty much constant. Which it looks pretty nice on there if you look at from the simulation. If you focus just the middle part of this whole thing, it looks pretty constant. Look at the arrow. It seems like the size of the arrow is still pretty good. All right, so that's fine. So that looks pretty neat. Okay, so that's how it's done to calculate the electric field from a two-dimensional sheet of charge. And I hope you understand this one. But then, John, wait a second. It's sort of understand now, but then why you put this in the box? The factor 2 is not here. Something is missing. Something is missing. And here comes the reality. Okay, what we applied or what we just did over here is just a two-dimensional sheet of charge. Like it's like a free floating charge. So electric field come out in both directions. But in reality, here we go. When you want to bring in the conducting plate, a real plate, it's not like just a flat sheet of something that is super flat. It needs it must have some thickness. Yeah? So that means in reality, the metal that you bring in must have some thickness like this. You cannot avoid it. So the question is, in the conducting plates, like you bring in like aluminum, copper, iron, or whatever, and once you put the charge on it, where will the charge go? It's not like a solid piece of the spherical ball that we learned from last time, because from last time we assumed that the charge are distributed across the mass, internal mass of this whole piece. So it means the charge is spread around uniformly. But in the conducting material, the charge is sort of like charges are free to move. So if you allow charge to move freely, where will they go? So you have to imagine this like playing games a little bit. Imagine that you are charges, and let's say you come into a classroom, and let's say you are free to move, you can fly pretty much. The classroom is just the conducting material. But then you and your friends are electrons. Let's assume electron for realistic scenario. So let's assume it's a positive charge, right? Even though in the reality it's an electron. Okay, let's think of positive. So let's say you are a positive charge. Your friend are another positive charge. Positive. Everyone are positive charges. Then you came into the room, seeing your friends. By Coulomb's law, the same types of charge will repel each other all the time. So this means you cannot stay close to your friend, because by Coulomb repulsion, you're going to push apart each other. Everyone will bounce around because you cannot get close to any of your friends. Where will you end up if you want to sort of like stay still? Like, I don't want to move anymore. Where this movement is going to end up with? The answer is you guys are going to end up with everyone will stuck on the walls, on the ceiling, on the floor, right? Because it's going to be the only position that you will not move any further. Does that make sense? Because you're going to keep pushing around until your back has to against something, and then you spread around that surface until everyone just sort of like, okay, spread out evenly, and then there will be no more movement. Everyone stop moving. So at the end, every time that you sprinkle charged particle onto a conducting material, those charge will distribute across just the surface of the material, because that's where everything is going to stop. Otherwise, it's still moving and you don't get static. There's no static analysis here. It's still moving. There's some, which we're going to learn next time. I mean, you still have some current and something is flowing. But anyway, this arrangement of this whole thing is going to go very quickly. So it just distribute until all the charges are distributed around just the surface. And remember what we did last time? We were talking about every time that you have a cage that is charged, the electric field inside is zero. Cool?
Okay.
Yeah, so that's why in the figure that you see over here, you don't see the electric field on inner part of the conducting material. You only have the electric field piercing outward from the conducting plates. So that's why the factor 2 just missing over here, because you drop the electric field. When you say you drop the electric field, so electric field pretty much have only one side to go. So you don't have any factor of 2 to worry about anymore. Sounds cool? All right, guys. So that's pretty much give you the overall picture of what is happening. So electric field just coming out of this, and it's also coming out, but it's extended from the other side of the plate. Okay. All right. So that's what it is. All right. But anyway, in terms of the structure of the electric field is still the same. It's still point perpendicular to the surface of the conducting plates. So that's kind of cool. But the business is not done yet. Almost done, but it's not done. What we need next is we need a capacitor, right? So what we do is we're going to have this. Oh, maybe I just only need this. Can I do that? All right, anyway, I'll draw a new one. So you need two of this, because that's what we want to build is we want to build a capacitor. But on the other one now, you will have a negatively charged going around, which is fine. Cool. So the scenario will look almost exactly the same, except now electric field will point into it, because we already learned that electric field lines pointing towards the negatively charged particles. So on the right side, the electric field will point towards it, towards it, towards it, towards it, everywhere, 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 like that. Cool? So overall, don't forget, I mean, this electric field actually is going to come all the way from here. I mean, it's extend infinitely. It doesn't have to stop there. So electric field actually go out all the way here. Same thing with the red line here. It's just going to extend out right there. It's going to extend all the way there. Extend all the way there. Cool. You can draw this thing on your own. It's kind of fun to do. Okay. So let me move this thing toward the center here. There you go. So what we have over here, you notice something here now? Look on the left end of this. It's like playing games right now. Electric field from the red portion here, the positive part here, is point to your left. Look at the left side of this one. But from the blue is point to your right on the left side of this one. So what I'm getting over here is you get a cancellation on the left end of this conductor. Okay. Now look at the right side of this one. Electric field pointing to the right is the red vector, and the electric field pointing to your left is the blue vector. It's just the same scenario over here. So they are pointing in the opposite direction. So you get the cancellation effect again. And we already learned that electric field is supposed to be constant all across. So here, the only inner part of this one that you get a same direction of the electric field. They're both pointing in the same direction. So this is the addition. So they're adding to each other. So in conclusion, the only portion that you get non-zero electric field is just the area in between the plates. And it's going to be twice as big. You already got that one piece give you sigma over epsilon naught. And eventually you're going to get another one from that. Okay, so you just add them together. And that's what you're going to get at the end. Sounds cool? All right, but at least you get the whole concepts of what is supposed to happen around the conductor. So let's take a look at this. So what we want over here is now, another confusion that might happen over here is in reality, the way that you think about this one is, I think what I'm doing over here is just like composes too many things on top of each other. But I just want you to get like how can I say it? It's like a big picture of what is happening here. Okay. And what you have over here is just saying that what you get out of this supposed to be the net summation of the electric field around. It's like everywhere, everywhere. However, the actual calculation can be simulated as well. So let's come back to this. Here we go. So what I'm going to do is I'm going to put another layer of this negatively charged, and let me put close by to make things close to our assumption there. Ooh, ooh, ooh. There you go. All right. So, using pen is a little bit better. All right. So I'm going to try to put them in a very uniform manner and have the same amount relative to the positive charge on the left. Playing this is kind of fun. All right, you start to see the construction of the electric field around. Start to build the electric field around this. See that? Oh, that's a maximum charge that I can put on. All right, very cool. So this is what happening here. As you can see, that the electric field from the left and from the right. Hey, how come it doesn't show the cancellation though? All right, but anyway, let me put the sensor in between here. Electric field supposed to point in the one direction in between, right? But then out here, wow, it still go in the same direction. How come it's not canceling each other on this simulation? That's so weird. Oh, is that I'm bringing them too close? No. That's really weird. All right, maybe this simulation is kind of realistic because in reality, wow, that's weird. Doesn't get well. I think the density is too low, so that's why you won't get the cancellation that I really want. Interesting. All right, but anyway, so you can see that now the electric field in between the plate is kind of straight, pointing from positive to the negative. So that's fine. But in theory, as long as we assume that the charge is big, I mean, the plate is huge, and the electric field that coming out of it is no dependent on the distance, you're supposed to get a perfect cancellation of the electric field from both sides. So that's what it is. I thought it's going to look smaller on the left and the right side of this, but it's not. Well, that's okay. All right. It's still big, actually, yeah, but it's diminishing over here, as you can see. The electric field is not as strong, but once you get in between, the arrow is just shooting out all the way. Okay, so this is a realistic one, but in the reality, the charge density is super high. So the cancellation, hopefully, is much better. All right, then. So that's what we have. And that's the conclusion that we're going to get is we can figure out the electric field, right, in the space in between can be found from thinking of it like you have a plate over here, which is a positive plate, and you have a negative plate over here. There you go. All right. And what you get over here is we already got from the knowledge of the previous exercise that if you're thinking just a pure simple plate floating around, the electric field is sigma over 2 epsilon naught. But then you get another contribution from the negative plate over here. So let's pull a positive there, and there's a negative plate, but it's the same magnitude there. So when you add these two together, combine, then the electric field in between is a sigma over epsilon naught. Cool? All right. And it's the same concept, or I mean the same argument if you think in the realistic sense that if you have like a conducting plate, the only charge that's distributed is only going to happen only on the surface. And then when you do the Gauss's law, then you ignore E inside, then you only have the E outside, and you get sigma over epsilon naught as the result as well. Okay, so anyway, don't worry about this one too much in the sense that
Okay.
I just want to show you how it's done, but in the exam or in anything, you don't need to do this anymore. It's just I did it once and it's done. All right, so that's good. So conclusion that we get from here is the electric field in between the plates is sigma over epsilon naught. Isn't that cool? All right, that's what we have. Right now, once we get that value over here, now we move on to the second step. What we just did over there has already completed the step number one, how to calculate electric field using Gauss's law. And now the second step is I'm just going to take this electric field and calculate the potential difference, right? Based on that knowledge here. Oh, the slide doesn't move. What's going on? Something stuck. No. Oh, it doesn't go. Oh, it crashes. Reconnecting. I don't know what's going on. Oh, 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 oh. Okay. I think I have to share it again. All right. Here we go. It must be disconnected. Okay. All right. Here we go. So what we have next is based on the known value of the electric field between the plates. Now, next step is I want to figure out the potential difference between positive and negative plates. How to do that? I'm just going to apply this definition of the potential difference based on the electric field right away. So what I'm going to do is this. I'm going to walk from the negative plate, walking. When I say walking, mean I'm considering the path pointing from negative plate to the upper positive plate along the green path. And what I'm going to do is I'm going to do the integral over here. So that's mean my displacement vector is going to point upward. But now we already learned that electric field is pointing down. E vector is sigma over epsilon naught pointing down. Okay, so no big deal. So it's mean electric fields point down, your displacement is pointing up. They're making 180-degree with each other. So my delta V is by definition negative E dot displacement from initial point to final point. That's how we calculate the potential difference between 2 points on the field. Now, negative sign is there. E ds cosine 180. Cool. But electric field is constant. I can pull it out from the integral. Cosine 180 is -1. So negative cancel with the negatives. I left with just a positive sign and integral ds. Woo, almost done. What is the integral of ds from initial point to the final point? It's just the distance between the plates. So if you know that the plates has a separation of d, that is just ed, which makes perfect sense.
Okay.
Why? Because you already learned that back in the day, energy is mgh, right? Gravitational potential energy. And if you ignore the m, that think of it as like a v, right? We didn't define v back in the day of the gravity, but in the potential, electric potential, v is just defined as the energy per unit charge. So if you can think of v in the mass, v is going to be energy per unit mass. So is it gh? So g is like e, h is like d. So there's no doubt the formula will look exactly like this. Because what you have over here is you have like gravity is pointing down, E is pointing down. And you say you want to go from the initial point to the higher point. What is going to be the potential difference? Is mgh or QED. But then you take Q to be 1. That's how you get to the potential, not the potential energy. So this formula looks perfect. All right, so that's it. So it's been known the E. Now you know that the separation is D. The potential difference is just ED. So the step number 3 is, yeah, C is just charge per ED. Okay, but E is already calculated from part 1, which is sigma over epsilon naught, which is fine. I just substitute that in there. So I can flip this epsilon naught to the top. Q is there, sigma is here, and the D is there. But now here comes the good part. We already defined the sigma to be charge per area. So the charge must be canceled. And I can flip the area to the top. And that's it, guys. That is my capacitance.
Okay.
Cool. That is done. All right. And that's the result that I put in the box right here. So I hope this streamlined the whole process of how to calculate a capacitor from a from the first type of capacitor, a parallel plate. And I'm gonna discuss about the property of this one after the break, but at least it's done. The three steps process is here and it's done. Very cool. All right. So let's take 10 minutes break if you still around. You still okay with me, yeah? All right. So if you're still around, then after the break, I will explain, sort of like give you some observation of what we got from the result here. And I am going to show you that now we can do one more type, like in a spherical capacitor, then they're going to look exactly the same. And things it's going to be much easier once you do it second time. All right. So let's take a break right here first, and we'll see back in 10 minutes. Okay. Okay, so we are going to do this whole three steps process one more time, but now we are going to apply to a spherical capacitor. And you'll see that now once you already saw once, this one is going to be a lot easier because now we get back to the spherical symmetry one more time. So the symmetry of the problem is now spherical. So it's good. So let's try how we can apply the step number one. The concept over here is going to be same thing, except that now the electric field is going to be pointing from positive to negative, right? So it's going to point something like this. And we can use the same arguments that away from this, you're not going to have any electric field outside because, if you look at it, you have positive and negative charge, right? And based on, you can think either way, Gauss's law or whatever, then you can assume that the electric field from the inner sphere and the outer sphere will cancel each other out. So we can assume, or it doesn't have to be assumed, actually, you can show it by doing the Gauss's law. So I draw this one roughly here. If you try to build like a Gauss's sphere outside, and you do just what we did like 5 times in the previous lecture, try to calculate the electric field on that green sphere, that will be 0 again because the net electric field, the net charge inside this Gaussian sphere is 0. Does that make sense? Okay.
Okay.
So it's the same idea that we can pretty much use in any capacitor over here, that you can assume that electric field outside is 0 everywhere because of the cancellation effects from positive and negative portion of the capacitor. All right? Approximately, it's not too bad. All right, it's fine. And in the spherical case, it's perfectly 0. Okay, so how can we figure out the electric fields between these two concentric spheres? So once again, by spherical symmetry, we are going to build a spherical, can you see this? A faint one here. There you go. Let me put it at the center here. There. So I'm going to build a Gaussian surface. Okay, let me put a green one and maybe it's easier to see. Here we go. So there. There you go. So my Gaussian surface is, it's in the form of a sphere, of course. And I'm going to calculate flux on this to figure out the electric field on this sphere, just like what we did before. So it's going to be integral E dot dA across this Gaussian sphere. And the same argument goes with electric field and area vector are pointing in the same direction. Area vectors always point in the radial direction outward. Electric field, you already saw, is going to point radially outward as well. So that means EDA are going to be followed by cosine 0, parallel to each other. Okay. And due to the spherical symmetry, electric field strength is supposed to have the same value in all direction. I can pull E out from the integral. You are left with just the integral of the dA. And the sum of those dA across the sphere will get surface of a sphere, 4 pi r squared. This is going to be the sixth time seeing this, right? All right. So with that, then you already learned that, Ajahn, you said that to the charge inside this Gaussian surface divided by epsilon naught. Okay, how much charge you are talking about when you look at this one, Ajahn? It's going to include that positive Q charge there. So just plug in the positive Q charge there. And as expected, the electric field supposed to be in the same form as the Coulomb's law. Does that make sense?
Okay.
Because we already discussed that no matter it's a point charge, it's a solid ball, it's a spherical shell, as long as you are away from it, you're not inside, the form of the electric fields will look all like Coulomb's law. And this is that case right here, right? Even though beyond that one, you have another negative Q waiting for you, but at least the electric field in between still have a Coulomb shape. All right, so that's it. Step number one is done. Even though if you don't want to execute Gauss's law, you can say it's supposed to look like Coulomb's law, KQ over R squared anyway. All right, now with that electric field known from the step number one, step number two is I'm just going to do the same thing. You want to walk from one point to another point and find out what is the potential difference between these two concentric sphere. So to make things simple, I want to walk from the inner shell to the outer shell. So the inner shell will be my initial point, outer shell will be my final point. Sounds good? The reason for that, the reason I say I have to emphasize that I'm going to walk in this direction because it's walking outward and it's going to be in the same direction as the electric field that's already pointing outward. So that's kind of nice. I know that my displacement vector is going to point. Oh, I don't know. Can you see it? It's green. It's hard to look at the ds. Okay. The ds, the displacement vector and the electric field vector will be parallel to each other. But by walking from positive charge to the negative charge, I'm walking downhill because I'm going from high potential to a lower potential, right? Walking from positive portion of the charge to the negative one, I'm going to a deeper potential value, smaller, I mean, more negative potential value. So I expect the final results to be negative value in potential difference. Cool?
Okay.
But that's make my vector calculation a little bit simpler because E and ds are pointing in the same direction. Okay, so I'm going to go for it. Potential difference is negative integral of E dot the displacement that I'm walking from initial point to the final point. So, and that will be equal to negative E ds cosine 0 from initial point to the final point. Cool. But then what you can see over here is because everything is in the radial direction. So my ds over here is going to be my dr in the r hat direction. You hate this one. But we already discussed about the r hat. It's just a radial direction, but it's a unit vector. So I can say is the displacement is change in the radial direction, the radial value dr pointing in the radial direction r hat. But this one is pointing in the same direction as the electric field vector. So that's fine. Cosine 0 is good. So this one I can say it's going to be integral E dr. So far so good. All right. And now I can start from radius equal to A, that is the radius of the inner ball, to the B, that's the outer shell. Now I can start doing the integral. Electric field came from step number one right there. So it's going to be 1 over 4 pi epsilon naught Q over R squared dr from A to B. Isn't that cool? Everything is under variable R. Everything can be done now. Q is constant, can be pulled out. 4 pi epsilon naught is can be pulled out as well. Now 1 over r square integral, that's what you have left to do from A to B. And of course, everyone knows how to do this because r to the negative 2 integral is a 1 over r negative. So that's fine. Negative q over 4 pi epsilon naught, negative 1 over r from A to B. Nice. And that's it, guys. I can leave the negative sign there. Substitute the upper limits and lower limits. So it's going to be, all right, because there's a negative sign there. So that it's going to be 1 over A minus 1 over B. That's what it is. All right. And with the negative sign in the front as expected, because I already said that I know the, oops, sorry. I know that the final result is going to be negative because I'm walking from positive charge to the negative charge. So as I'm going downhill. So delta V is supposed to be a negative value. So the actual potential difference between the two is just this value right here. I only want the magnitude of the potential difference, right? I don't need a negative sign with me. So I'm just going to grab the one in the red box there to be my delta V to use in the third step. Sounds cool?
Okay.
All right, so that's my potential difference, right? So the third step is the easiest one. You take the Q divided by the delta V. So that's it. So C is Q. Right now in this figure is the capital Q divided by the delta V that you just got from the step number 2. All right, just bring the whole thing there. I can do the common denominator and everything. So it looks like B minus A over AB. Now, one thing that's nice, Q cancel again. All right. And what I have here, I can flip that 4 pi epsilon naught to the top. I can flip AB to the top as well. And I have B minus A at the end. And here we go, guys. That's the capacitance of
Okay.
a spherical capacitor. So I hope by showing you these two uh, geometry of the capacitors with the 3 steps process calculation, you can repeat this to any kind of capacitors shape, and you should get to the value of the capacitance this way. But we're not going to do anything acrobatic or anything. It's going to have one last geometry for you to do is the cylindrical. And that's it. I'm going to leave this one as the exam question. Okay. So in the exam, I'm going to ask you to calculate the capacitance of a cylindrical capacitor. Just show me it doesn't have to be exactly 3 steps process, but just show me how to calculate the capacitance of a cylindrical capacitor. So, the final answer is going to be this one. So it's just like verify or show how to calculate the C for the cylindrical capacitor. That's it. So this is like I already told you one question in the exam. It's going to be this. All right. So what kind of characteristic of the capacitor that we can observe from the results that we got? So back in the first case, we saw that, hey, Ajahn, this is the capacitance of the parallel plates capacitor. See, it depends on the A and the D. See that? The A is how big is the plates. The D is the distance between the plates. So what you have looking at right now is it depends on the shape of the capacitor. Are you sure? Well, yeah, let's take a look at this. Well, the results from the spherical capacitor, it depends on here. The only parameter in here is just the inner and outer radius of these spheres. So the only way that you can change the capacitance of this capacitor is just by changing the size of these 2 spheres. That's how you change the capacitance. Same thing over here. The only way that you can change the capacitance of this one is just changing the size of the capacitor. Size means it could be the size of the plate or the distance between the plates. So this is a conclusion. The capacitance depends only on the physical parameter or the shape, the physical shape of the capacitor. So things will change when the physical parameters or physical shape of those capacitor changes. And this one is very obvious in one of the devices that you use almost every day, and that is the keyboard. The keyboard actually is the capacitor. So on each key, if you tear it down, look inside, there will be a construction of like a two plates capacitor. It's like a two conducting plates. It doesn't have to look shiny or anything, but those are the thing. And every time that you press a button or a key on the keyboard, you change the spacing between those two conducting material. So the capacitance of that key gets changed. And that's how the PC or your computer can detect which key on your keyboard is being pressed. See, isn't that cool? All right. And the same thing with the touch screen on your smartphone. You use, I mean, that's use the same technique, even though it's just more complicated. But on the screen, on each pixel, there will be a construction that look just like a parallel plate capacitor like this. And then the thing is, when you have a finger around, and compared to when you don't have any finger around, the capacitance on that pixel is going to change. So that's why you change the physical parameter or physical, stuff around it. And that's how your phone can detect which pixels on the matrix on the panel get finger on. And you can now drag around and you can do pin zoom, or you can do multi-touch now because you don't, any points on the screen that get touched, the capacitance will change around that. And then you can have a chip to process the location of your fingers. Sounds good? All right. So that's why the screen on the cell phone is it's saying on the specification is the capacity touch screen because it's detecting the capacitance changes on the pixel on the screen. So cool. All right. So I hope this one sort of give you an idea. And this is a quantity that's sort of like stay around you all the time. Back in the day, I don't know when you were young, where you were like still a kid. I think you still use the antenna on the TV. Yeah. And you still remember that you have to adjust the location or the orientation of the antenna. And every time that you touch it, sometimes it's like the image and everything on TV is nice, and then when you let it go, it's fail again. Or maybe just somebody walk by and then the image is already just go crazy and all this stuff. That is because having your hands on the antenna and not having your hand on the antenna change the physical parameters or physical value of that antenna, and that make capacitance changes as well. So that's what it is. All right. So that's why this capacitive uh, parameter is very, very, I mean, is being used in the today's technology a lot. Okay. And actually, that give you a screen that made out of glass, because by having this capacitive touch screen, then you only have to be around. I mean, your finger just have to be around. It doesn't have to touch. So that's why you can have another glass panel on top, and then you can still detect the capacitance change anyway with your fingertip on it. All right. And if you still remember the Nintendo DS, that's like you have a pen that you have to press on it or something. You will feel that the surface of the Nintendo DS back in the day is soft because that one is a resistive touch screen. So you have to put a dent onto the screen to change the resistance to detect the location. That's why. Okay, sounds cool. All right, so I hope this summarized things that's, I mean, it's kind of good application of the capacitance and all this stuff on here. All right, guys, that's it. I think that's all I want to show you, and I think I already told you the question that is going to show up in the exam, and just study that problem, which is already in the textbook everywhere in this universe here. Should be good. All right. So I hope this is not too heavy for today's lecture, and I will see you for the last lecture on Saturday. Is that right? Saturday. Yeah. All right. Okay, good. Okay. So we have one more lecture, the last lecture on Saturday afternoon. Thank you for sticking around. All right. I'll see you on Saturday. Okay. Thank you, Crab. Bye bye.